Hi, my name is Brighton Cooks, and this is my Physics 2211 Lab 2 presentation. To start off, here's our table of continents, what we're going to be going through during this presentation. So to start off, our introduction. The instructions of the lab were to observe the motion of an object that is dropped from rest and falls straight down somewhat slowly. The purpose was to measure the object's motion after being dropped with two computational models. Some fundamental physics principles that are present throughout this lab are Newton's second law, gravitational force, and drag force. As a brief preview, we saw that the model that considered gravity and drag was more similar than the model that only considered gravity when compared to the final results. So, some physics principles. Number one's going to be drag force. This was a new one that we kind of had to play around with, especially with our code, and we're going to get into that whenever we look at the code. But drag's going to be a force that acts against gravity, so while gravity pushes down, drag's going to be pushing up. So gravitational force, obviously the big one, it's going to cause the ball to fall. It's going to be negative mass times the force of gravity. And obviously we're on Earth, so the gravity is going to be 9.8 meters per second squared. And then Newton's second law of motion, that kind of just allows us to get velocity and position acceleration. And Tracker is able to do this for us. So system and surroundings. The object I used was a regular ping pong ball that weighed 2.7 grams and had a diameter of 40 millimeters. In this experiment, the ping pong ball was the system and everything else was the surrounding. Some of the outside forces acting on the ball during the experiment are gravity and drag. Procedure. Here's the video of me dropping the ping pong. Yep. And then above it is some of the graphs we got through Tracker. For this experiment, the object I chose was a ping pong ball. Using a gray background, I recorded the ball falling straight down, and because it's a daylight object, it falls slightly slowly. This recorded its change in position over time, allowing me to find the velocity. I used the application Tracker to automatically compute the object's velocity for me. Then I plugged my results into another application called GlowScript to measure what the data would look like if there was no drag. The initial conditions of the experiment were velocity of 0, the position of the ball in the video, and a mass of 2.7 grams, and a gravitational force of 9.8 meters per second squared. So this is my code. As you can see, I'm going to be on line 54. My drag component is going to be 0.00. The code being worked as create an appropriate model. And then, so you can see some of the formulas we used. We added gravity and drag to get the total net force on the ball, and then some of the formulas we used for velocity and position, and our results. What the code just showed, we got our results. Our particular model on the left is a particular model without drag. It makes complete sense. It's a linear function that is increasing at a velocity of -4 meters per second squared, and that's exactly what a ball should do when it's dropped on Earth, and it negates all other forces. However, the world isn't perfect, and the force of drag acts against it. So on the right model, you can see realistically or more realistically what a ball would look like. Ball's not so linear because